So April 27th, I believe it's a Thursday, right? The project problems are due the 23rd, which will be the last day of class, and that day will just be a review for available to ask questions, and as like the midterm, the exam will be completely drafted by that point, so you don't have to worry that any questions you ask will change what appears on the exam. Okay, so today we sort of wrap up the time-dependent deformation behavior. So we talked about viscoelasticity, and then last week we discussed creep and crystalline metals. And so today we're actually heading back to the polymer world. In some ways it would have made sense for this to immediately follow the viscoelasticity lecture, but we never actually typically get this far, usually. But because I made some of the changes to things we taught earlier and shifted some content around, this is actually material that normally sort of hasn't been covered in this class before. And I think next year I'll rearrange it a little bit. But so just as a reminder, we had previously talked about linear viscoelasticity, right? Which by that we meant that the creep compliance and the relaxation modulus are independent of stress, meaning that if we have a creep experiment and we double our stress, all of our strain responses are scaled by the same factor that we increase our stress. And when we talked about this, I focused primarily on it from a phenomenological point of view, right? There wasn't a lot of material physics in there. So today we're actually going back and looking at some of the actual polymer interactions, right? The chemistry of the polymer chains and the structure of the polymer chains that give rise to this behavior. So if we remember here, if we look at our relaxation modulus, right? Remember at short times we have basically what in the polymer world we call glassy, meaning a hooky and elastic response. At very long times we have a viscoplastic flow, and in between we have this decreasing region of viscoelasticity, and then a lot of materials, this rubbery plateau. And we didn't really discuss it before, but this rubbery plateau is really a function of the structure of the polymer, particularly molecular weight. Right? If we have long molecules, right, they're going to tend to entangle, right? Just as we talked about when we were discussing yield in polymers, right? And this is going to give the formation of physical links that restrict the molecular flow through the construction of these temporary networks. And remember back when we did rubber elasticity, we said not all crosslinks are created equal, right? Some links are temporary slippages versus pure chemical crosslinks, right? And we discussed how modern rubber elasticity theories like the Boyce-Arruda work and the Ball, Doi, and Edwards models accounted for this, whereas the Mooney-Rivlin model that we talked about and other models assumed a fixed distance between these crosslinks, right? So it all ties back to our theory of rubber elasticity and our theory of polymer yield and flow, right? But if we have long times, we're considering a load that's active for a long time, especially an elevated temperature, right, these physical entanglements become labile and lead to irreversible flow, right? They're not permanent. They're these kind of slip links or chain rearrangements can then allow further flow. If we have permanent chemical crosslinks, like in vulcanized rubber, right, our quintessential elastic material, the modulus of this rubbery region tends to increase, right? So this rubbery or leathery region is directly related to sort of the equivalent molecular weight, right? How entangled things actually are. So what we can see here, this is experimental curves from from PMMA. I'll have the structure of that in a bit when we talk about some of the side chain reactions. But a low molecular weight and a high molecular weight. And the low molecular weight, we don't see this this plateau region, whereas at high molecular weight, we do, right? Remember, this is a log scale here for time, so this is significantly compressed. If this was a linear scale, this plateau would be very extended. Right? So we see basically at these times, potentially, depending on how fast this goes down, an order of magnitude difference in the relaxation modulus as a function of the molecular weight. Excuse me. Yeah.
Which one was the low molecular weight?
This is the low molecular weight, right? And so these are a factor of 10 difference in terms of the molecular weight. But notice that essentially the elastic response is the same, right? The short time, right? The high frequency, right, doesn't deviate. It's the holding for long periods of time, right, where you're going to get significant differences due to the change in molecular weight. So we looked at glass transition, right? If we look at the modulus as a function of temperature as we cool it down, we see a region where we get a sharp increase in the modulus, that we call this as the glass transition temperature, and then we have secondary transitions that happen at lower transitions, and lower temperatures. We didn't talk about these secondary transitions before, but these are related to mostly side chain interactions, and we'll talk about them in just a little bit. Example, this is a schematic of the behavior of polypropylene, and it's the interactions between this methyl side group. Now, those of you who work with Professor Lanuti or Guan or Dr. Powell are going to have to forgive me on my organic chemistry. So I became a metallurgist, so I only had to take one organic chemistry course instead of two, because of the horror that was Orgo Lab. So if I say something dumb with respect to chemistry, please forgive me and correct me. Right. So polyethylene terephthalate, right? This nasty structure here, we got a benzene, but this, like a lot of polymers without long, bulky side chains, will crystallize when cooled slowly, right? So if we look at these, and the x's on both of these curves are our modulus, and the dots are the tan delta, our phase shift from the DMA, right? Between remember DMA, we give it a cyclic loading cycle, and we look at the phase shift between the stress and the strain response, right? So tan delta is going to be give us an indication of where we have the greatest viscoelastic behavior. Okay, so which of these is crystalline? Right, which one's amorphous? So we basically said on the previous one that a greater entanglements give a higher modulus, right? So which modulus is decaying faster? So wait, what's your answer? This one is.
This one is lower.
This one's right. This is faster, right? So at longer times, right? I mean, at higher temperatures, we get a faster decay of modulus here versus here. So which one's crystalline? The left or the right? No, so this is going to be, the left is the amorphous, right? Our crystalline interactions, right, are going to be the strongest types of chain, some of the strongest types of chain entanglements that we can have, right? So crystalline regions are going to severely hamper molecular mobility. Right? So we will have a stiffer, a higher modulus at a given temperature in a crystalline polymer, semi-crystalline than in amorphous, right? Notice a couple things though. Our tan delta peak appears at roughly the same place, right? Same sort of temperature, right? But it's much narrower in the amorphous than in the crystalline. So we have a wider window of viscoelastic behavior in a crystalline polymer versus an amorphous polymer. So if we consider just amorphous polymer, we'll use PMMA as an example, right? And so it's common sort of just convention in the polymer literature to label these transitions as alpha, beta, gamma, delta, right? Basically alphabetical Greek order, with alpha being the alpha relaxation is the glass transition, gives us our large change of modulus. The beta reaction has been characterized typically by NMR spectroscopy, right, with side chain interactions associated with this ester group, and the gamma and delta relaxations have to do with these interactions between these methyls, right? So generally, the general trend is as we go down in temperature, these relaxations that we see tend to be associated with smaller and smaller interactions, right? This ester is going to be larger and more bulkier, give you more steric hindrance than these small methyl groups, right? And this is loss modulus here. So when you're going through the reading, pay careful attention to what the graphs are actually showing, right? Because so the loss modulus basically gives us the amount of energy that's going to be dissipated by the viscous contribution of the behavior, right? So again, at temperature. So we have near the glass transition, a higher degree of viscous flow. As we cool down, we get some less. Increase, decrease, increase. This is why polymers confuse me, right? You get these strange strange behaviors. So the glass, from a mechanical point of view, the glass transition is much more important than those secondary transitions. We're not really going to worry about those much anymore. The factors that are going to affect the glass transition are really the main chain structures. Right? So the more flexible our main chain is, we're going to have a higher degree of flexibility with our chain, and we're going to reduce the glass transition temperature. Right? And the opposite effect is going to be the introduction of a largely inflexible group. Right? So these ether links, right? This is one of the few things I remember from organic, right? The ether bunny. Right? Right. So you've got that oxygen with two side groups coming off here. Right. This is has a more significant degree of freedom than these terephthalate type structures, where you now have these big benzene type rings. This gives you a more rigid polymer chain, and is going to have a higher glass transition than a more flexible chain. Right? Side groups also can have an effect on the glass transition. Right? Bulky, inflexible side groups are going to tend to increase the temperature of the glass transition. Right? So if we look at the family of polyolefins, right, and we look at what the side group is, if we go from a polypropylene, which has a simple methyl side group, up to this nasty looking structure here with some vinyl, I don't even know how to describe that. But we see a 200-degree change in the glass transition temperature, right? Simply because these large molecules, these large side chains, can't get out of each other's way. Right? That's really all what it boils down to. Right? If we make these side groups longer and longer, right, we increase the length of flexible side groups, we reduce the glass transition. Right? So basically, here we have side groups that become longer and longer chains, and we see the glass transition. But notice these are linear chains. These aren't the big bulky things. So these have the snake-like kind of motion that can get out of each other's way. And so basically, as we increase the number of these chains, we can reduce the number of methyl groups in our side chains. We can reduce our glass transition. Right? And of course, it is going to depend on the structure of the main chain itself and the structure of the exact side chains, how drastic that is going to be. Right? The last sort of structural thing that we need to worry about is the main chain polarity, right? How polar the bond is, right? So polyethylene, right? Just right carbons with a whole bunch of CH2 strung together, right? Very nonpolar, right? And so we're going to have a lower glass transition than something that has a higher polarity, stronger interatomic forces, right? That's going to give us a decrease in chain mobility and a increase in the glass transition. Okay, so I don't want to embarrass myself more by going into deeper details of polymer structure, right? Other than those sort of main trends to keep on point. But in reality, it all comes down to the simple idea that the more interactions that you have, right, the harder it is the more likely you are to form physical links, the higher your glass transition temperature is going to be. The more flexible and easier for the chain to move, the lower your glass transition temperature is going to be. Right. Okay, so when we talked about viscoelasticity, we did not explicitly talk about a temperature dependence at all, right? So here we need to bring that in, right? And there's some practical and scientific aspects of the temperature dependence that we want to think about. From a practical point of view, it's not typically possible from a single experimental technique to measure the complete range of frequencies, right, to evaluate the relaxation spectrum at a single temperature, right? If we're talking about frequencies, that some of the plots we looked at went out to 10 to the minus 6 seconds, right? You really can't measure enough cycles, right, to ever actually do that with a sort of static loading frame, right? So the idea is we change the temperature of the experiment to bring the relaxation times within a time scale that's readily available by our measuring equipment, right? Of course, this assumes that we have some sort of simple relationship between the time scale and the temperature, right? So what does that mean with respect to mechanisms, right? We have to think carefully about that, because if we have very different mechanisms happening at different time frames, we can't do this. So why didn't we talk so much about a time temperature superposition with metals, right? We looked at the deformation maps, right? The Ashby type maps, right? And we had very different mechanisms, right? Active, right? We had dislocation glide, climb glide creep, diffusional creep, right? Grain boundary sliding mechanisms, even within the superalloy, right? And we looked at the intermediate temperature range. We had shearing versus climb bypass and formation of different faults, right? So if we have big changes in mechanisms, with more importantly changes in activation energy, we'll see that we can't easily apply this kind of notion. From a scientific point of view, right, we want to obtain a molecular interpretation of the viscoelastic behavior, right? What was our molecular interpretation of the rubber elastic response, right? What primarily drove that, right? Was it internal energy or entropy? Entropy, right? And we talked about random walk processes and chain statistics and a number of possible conformations. So we have a molecular theory of rubber elasticity. Now we want to be able to obtain a molecular interpretation for the viscoelastic theory, right? And we know that polymers change from glass-like to rubber-like as either the temperature is raised or the time scale of the experiment is increased, right? So at low temperatures or high or very short times, we want the stiffness to relate to the changes in the stored elastic energy, right? Makes sense, right? Because we don't have any permanent flow, right? At the rubbery state at high temperatures, right, we have molecular chains that have a lot of flexibility, right? So they can adopt conformations that lead to the maximum entropy or a minimum free energy type state. So we have to find something that balances these two considerations out, right? So this rubbery-like state, our deformations are really going to be associated with changes in molecular configuration or conformation. I have to be careful because configuration and conformation mean very different things to polymer. Right? So here we have time temperature equivalence, right? So J, this is compliance or modulus, right, from our notation. Right? This is compliance. Right? So which of these is at higher temperature? Think about it for a second. Do you expect it to be more compliant at higher temperatures or less compliant? More compliant, right? So a faster creep deformation at higher temperatures, right? So basically the idea here is we measure the compliance as a function of time for multiple temperatures, right? These curves can then be shifted to where they overlap and plugged together to form a master curve, right? Then, based by the amount that we have to shift these to bring them into coincidence, we know what the shift is going to be as a function of temperature, how we have to move this curve as a function of temperature to get our creep compliance for our temperature of interest, right? So we want to record this variation of the shift factor with temperature because this is an important validation for whatever theories that we come up with, right? Does our shift going to match what was observed experimentally? Right? And by now this should look fairly familiar, right? This nodal theory, we have a molecule that can sit in two different conformations with different energies. Right. We consider the probability of going from site 1 to site 2, right? It's going to be a function of the activation energy that needs to be overcome, right? Versus going from site 2 to site 1. So of course, we're more likely to transition here from site 2 to site 1. And the probability of these transitions are going to be linear with our activation energies here. But if this is a mechanical process, right, we're going to assume that the energy difference between the two sites is going to change by the application of stress, right? And the strain is going to be a function of the change of populations from site 1 to site 2. So how does this work for polymers? It's pretty easy to think about in metals when we're talking about diffusion creep, right? In terms of vacancy diffusion, right? Hopping from one atomic site to another. It's a little more abstract when we're thinking about the motion of these big these big sorts of change, right? But we can think of example that is discussed in the reading, right? We can think about these polyethylene, right, in a gauche configuration where the carbons are on opposite sides versus a trans where they're on the same side. So we have a chain road. These sites can be rotational configurations that allow chains to move past each other. Right? Okay. So we're going to do a little bit of algebra now. Right? So if we assume that our applied stress causes a small shift in the free energy, right? So this is our free energy change. This is our applied stress. Right? This is going to have the units. This parameter is going to have the units of volume to make everything balance out. But we can rewrite our transition probabilities in terms of the stress. Right? And now we can go through just like we did before and do rate equations for site 1 and 2, and then combine them together in terms of a total change in occupancy, this little case n here, as a function of stress and temperature. And so we get a differential equation that links our change of occupancy with our stress and temperature. So we have to make another assumption and assume that our change of strain is due to a change of the site occupancy. So our total strain we have broken up into a unrelaxed strain, or our instantaneous elastic response, right? Our Cookean elastic response, and then the strain due to these change of conformations, right? Where this is our site fraction. Out front, and if we consider what we have here for our previous slide for our transition model, and we look at the strain that we derived for a Kelvin-Voigt model, we basically, people said, oh, they're the same form, right? We have differential equations in the same form, right? Just a reminder that the Kelvin-Voigt is a spring in parallel with the dash pot. And the relaxation time of the Kelvin-Voigt model is 1 over that B parameter. So if we have our equations that are of the same form here, right? Our B parameter looks kind of nasty like this with these exponentials and the difference here between the activation energy. But if we assume that the relaxation time, this RT, not relaxation time, our gas constant times temperature is small compared to the equilibrium free energy difference. We simplify out to something, again, that looks pretty familiar. Nice exponential relationship, right? And the relaxation time we can use to relate our frequency of jumps between these rotational states. Right? And at the end of the day, what we come down to is the big message is that the frequency of these changes in chain conformations is really just a function of the activation barrier, right? Rather than the actual absolute free energy difference between the states, right? So first approximation. And this makes sense, right? If we have a huge activation barrier, even though we have a big change in free energy, right? A big lowering of free energy, we're not going to be able to overcome this, right? So we end up back with something that makes sense. So this seems kind of a convoluted process, right? So essentially, right? Why did we go through this? Basically, what we're trying to do is we had this Kelvin-Voigt model that was purely empirical, right? And now we've been able to look at it from a thermodynamic point of view and assign a physical interpretation to those parameters that we had before. So how does this help us get to our shifts, right? That was our big thing. Why did we start this out, right? And at the end of the day, we come back to something that's Arrhenius, right? These are equations we're completely familiar with, right? So because it's Arrhenius, we can use our classical thermodynamics to determine this shift factor, right? We have here a change in enthalpy, right? Our frequency of jumps between these states is related to an enthalpy term. Right? We know how to relate enthalpy to the frequency and temperature, so we can think about our changes in frequency at two different temperatures, right? And extract the shift parameter. And then we can also, once we have our shift factor, we can relate the activation energy for the process by plotting this on a log of our shift factor versus reciprocal of temperature, right? And that will give us our activation energy for the chain relaxation processes of interest. Right? So it's kind of an interesting approach, right? We're starting with some simple thermodynamic assumptions and an empirical model, and making a generalization of how to interpret these shift factors, right? So what are the big assumptions that we need to consider? Is here we're really assuming that the relaxation processes have a constant activation energy, right? If activation energy changes, or we have a mechanistic change of these relaxations, this approach definitely won't work. Right? So an example of where this breaks down would be localized motion in the crystalline regions of semicrystalline polymers. Right? So this nodal site theory doesn't work, right? And the temperature dependence of glass transition relaxation in polymers does not always fit a constant activation energy, right? So that's a direct limit to the range that we can do this, right? We cannot use this to compare responses from well below the glass transition to well above the glass transition. Right. Another sort of approach is the Williams-Landau-Ferry approach. So this is looking at the storage compliance or creep compliance, right, as a function of temperature for this poly and octyl methacrylate. I couldn't find a nice picture of the mergers for this, so I don't offhand know what it actually looks like. But here they've measured the compliance from minus 100 and minus 14 to 130 C. And the observation is that at high temperatures, there's an approximately high compliance, this rubbery compliance. At intermediate temperatures, there's this frequency-dependent viscoelastic response, right? And then again, at low temperatures, right, we have a approximately flat, glassy response. And they took all this data and put it together, and this shows the horizontal shift factor as a function of the storage compliance, and I get a curved behavior that looks like this, right? So right at low compliance, right, which corresponds to low temperatures. Right, of course, we have a larger shift than at high temperatures, high compliance. But what they found is if they measured this shift factor as a function of temperature for a huge number of different amorphous polymers, they all fit this same relationship. All right? And they all had shift factor versus temperature curves that, when normalized, would fall onto this same sort of rule, right? Now, this is completely an empirical relationship, right? This was just done by curve fitting. Right? So this TS here is a reference temperature that's going to be different for each system, and these C1 and C2s are just fit constants. Of course, whenever we see an empirical relationship, the natural question is, does it have some kind of fundamental interpretation? Right? And so if we measure from dilatometry, right, our thermal expansion is a function of temperature, right? Remember, we see a change in slope near the glass transition. And of course, the faster the cooling, the less well-defined this point is, right? At higher cooling rates, this is much more of a smooth curve than an actual sharp point. But if we cool it slow enough, this TG really does approach a given point. I think in the reading I assigned, they said the difference between a cooling rate of a degree per minute and a cooling rate of a degree per day only gives you like a couple hundredths degree Kelvin change in the position of the inflection, right? So it is possible to sort of define a rate independent value of TG, and we can have a modified WLF where we put TG in here. Right? TG is generally proportional to TS. It's not going to be exactly equal to it the way that it was defined before. Okay. So where are we going? Right, we're basically going to try and do the same sort of thing and come up with a molecular interpretation for this WLF relationship, right? And come up with a reason why this completely empirical relationship has some sort of physical basis, right? So we're getting into a little bit of more polymer theory than I would like. But basically the idea here is that this occupied volume, the total volume can be split into an occupied volume, the free volume components, and this occupied volume increases at a constant rate with temperature over the range of interest, right? And at this discontinuity, the expansion of the free volume drastically increases, right? And the interpretation of this is that the molecular processes that control the viscoelastic behavior really begin to commence at the TG, right? And it's not really just where their time scales become comparable to other, with that in the measuring time scale, but it's below. We really don't have any viscoelastic mechanisms, molecular processes that give rise to viscoelasticity below this, right? It's also been taken by a lot of people to assume that this TG is actually a genuine second order thermodynamic transition, right? There's still a huge debate about that. So I don't even want to, I'd be very quickly in depths, well above my head if I waded too much deeper into this than is on the slide. But if you have questions, I'll be happy to find a suitable answer for you. Right. So if we consider a fractional free volume, right? So this is the free volume over the total volume, right? We can define that as the fraction at the glass transition plus a linear term, which is the difference between the current temperature and the TG. This is essentially very much like a thermal expansion coefficient. We can actually get to this WLF model by considering a Maxwell element, right? So before we consider the Voigt element for the nodal site theory, now if we consider a Maxwell element, we can actually get to this WLF model. Remember, the Maxwell element is a spring in a dashpot in series rather than in parallel, right? So which gives us an instantaneous elastic response, then a time-dependent viscous response with a large permanent offset. So here we're going to assume, the big assumption is that our changes in our elastic modulus or instantaneous elastic response is small compared to the changes in viscosity. Right? And we're going to bring in another sort of empirical relationship, this Doolittle's viscosity relationship, which is found to relate the fractional free volume with the viscosity. Right. So this ends up being a big sort of criticism of this approach, is that we're relying on a whole bunch of empirical stuff to try and make an molecular interpretation. But if we relate this shift to our recall F and F of G, right? This is our fractional free volume versus the fractional free volume at the glass transition. We can relate our shift as a function of our free volume. We then plug this in. We get something that has our log shift versus a difference between temperature and TG, and this is basically recovering the WLF equation, right? So we assume we can rewrite that in terms of a viscosity, and we get this. Right? So the WLF equation empirically makes a lot of sense from a perspective of talking about the Maxwell element. Right. Again, in my point of view, it still leaves a lot to be desired. This is still really empirical, right? At least with the nodal site theory, we had some fundamental thermodynamics, right? We had a fundamental mechanism. Here, we're just saying, well, we've got this notion of free volume change, right? And we assume that we're going to have certain molecular processes that become active here, that are not active down here, but are strongly active here, right? And then we say that our viscosity is going to be a function of this free volume, right? Making it an implicit function of these molecular processes. But we never talk about, nowhere in the literature about this does it talk about what those specific processes are, right? Again, at least with the nodal site formulation, we can talk about rotational configurations and an actual thermodynamic site jumps, right? And then we throw this all into how the viscosity is related to the free volume through an equation that a lot of people seem to take as more fundamental than a lot of others, right? Some people in the polymer rheology world sort of take this as a sort of a given. Others say free volume models are garbage and you can't trust them and you have to go back to very classical fluid mechanics type things. So from a personal perspective, I find this sort of unsatisfactory, right? But it's sort of a cornerstone of this time temperature dependence. Okay, so we have a couple slides that we're going to wrap up on Wednesday on nonlinear viscoelasticity, right? And remember, so in linear, we said the compliance and the modulus are independent of the stress. For nonlinear viscoelasticity, the compliance, creep compliance, and stress relaxation modulus become explicit functions of the stress. So if we increase our stress, we're going to change our moduli values. So that means our Boltzmann superposition doesn't hold, and all of the analysis becomes really nasty really quickly. And the focus is not going to be on how to do the analysis, but the focus is on that once you enter nonlinear viscoelastic regime, the world gets really bad really quickly. And that's why we spend so much time focusing on linear models from a theoretical point of view. Right? This is something that in the polymer mechanics point of view, right, there is not a lot of fundamental physics that describes nonlinear viscoelasticity. It's a lot of empirical models that make changes, small changes to the linear equations that we look at. So, okay, so let's get moving, and I'll wrap up very quickly. Nonlinear viscoelasticity right? The idea is linear viscoelasticity, the compliance, creep compliance and relaxation modulus are independent of the stress. So if we move into a nonlinear viscoelastic regime, the compliance and moduli are explicit functions of stress. The Boltzmann superposition doesn't hold. You can't just simply add up everything in the same way. The analysis gets much, much more complicated, right? And so the point of going through this is not so much for you to work through everything and try and do the analysis, but just to appreciate that the reason why we assume everything is linearly viscoelastic is because the nonlinear analysis just gets nasty very quickly, and you have to resort to simulation.
Is Q just the bulk modulus, or is that relaxation?
Oh, this is the creep compliance and the relaxation modulus, right? So the engineering approach is basically to tabulate your data and interpolate, right? This is the way most things are done. You do tests at different strain rates and at different temperatures, and then you put it all in a big table, and you let your finite element simulation interpolate between your curves, right? So this is how 99% of the analysis is actually done, because it involves a lot of testing, but conceptually it's straightforward, right? If you're interpolating, you have pretty good confidence that you're going to have something reasonable. Doesn't work so good for extrapolation, right? You go off the rails pretty quickly when you try and extrapolate from tabulated mechanical data. The other approach is sort of modifications of the linear theory, and you can either do that with differential approaches, where we take the differential equations that govern the different models, the Voigt, Maxwell, or the standard linear model, right? And you add an explicit dependence of the terms that you get on stress, right? So here's the differential equation for the standard linear model. What people have done is generalize this to this K here, an M here, and an arbitrary function of the strain here. So these K and M are functions of the stress. This is the stress response at very low strains, right? At essentially infinitely slow strain rate, right? So you have to pick a model for this, right? And this difference between the applied stress and the infinitely slow stress response is what's called the overstress, right? And our instantaneous Young's modulus is this M over K of these coefficients here. And we call this left-hand side the overstress, right? And so a bunch of models have been built using this approach. The most famous one is the Kitagawa model, and this is essentially in all of the finite element solutions. This they write explicitly as a function of the shear stress, so you have a shear overstress. And so they have a differential equation here. And what's the standard way, first approach, whenever you're given a differential equation when you're trying to solve it? Right? The tried and true way that you approach differential equations for the most part? Wolfram alpha? Wolfram alpha. Right. So see if a standard solution exists, right? Then the next thing is assume that it's a linear differential equation and make a guess of solutions with standard forms, right? So That's basically what they did here. So they expressed K here in this form, right? And then basically you assume a form for this K, then plot the value as a function of overstress. Then you can go back and solve for M, and then you end up with sort of a model that does a good job of capturing these sort of jump rate tests, right, where you change the strain rate in the middle of the tests and look at how the stress changes. And this is sort of a very difficult test to try and capture, right? But basically, there's a huge number of assumptions here, right? We just sort of pick the form for how we're going to handle the stress response. We pick the form for one of the two constants and then solve for the other, right? So that's the differential approach. And there's a whole bunch of different ways of looking at this. This starts from the standard linear model. You can use more complex models with more springs and dashpot elements and look at the equations that come out of those and then add in terms.
So how did the M come from the model?
What's that?
Okay, K is written here. So how did we calculate M?
Basically, you then take different. You know what this is. K, you have a solution for from experiment, and then you numerically evaluate a function for M.
But we don't know gamma's function of stress's function of strain before, right?
Well, no, you have tests. You have iso strain. You have iso stress. Other experimental data, right?
Okay. So you already know stress as a function of strain.
Yeah, you have experimental values for that, right? That give you your boundary conditions and under different boundary conditions, right? It's just very much a numerical thing, right? The idea is you have two unknown functions here. So we're going to assume a form for one of them and then use our data to fit a form for the other.
So how does the form for M will look like? That's a fit, right? So you have some form similar to this.
Yeah, I don't know exactly how it looks. Right. Then the other approach are this huge family of integral models, right? Where basically you make one approach. What Lederman did is make modifications of the Boltzmann superposition by putting a explicit stress dependence in. Pipkin and Rogers wrote stress as a function of the history of strain, right? And then if you do that, you can get what he calls a creep function, which is a generalization of a compliance term, right? And then basically it gets a heck of a lot more complicated from here as you go out, right? There's integral models with dozens of terms in there that are sort of all sort of fit. Right. Another approach is you can go back to in an analogous way that we looked at creep in metals, and you can develop the Eyring equation. Remember from PChem, right? It's about reaction rates in chemical kinetics, right? And you express your strain rate as a function of your stress and the thermally. This is the enthalpy of your activation, right? This strain rate can then be plugged back into the equations for all of your different models, and then you end up at the end of the day with nasty sets of coupled nonlinear differential equations that have to be solved numerically. Right? And so these are sort of the standard approaches for how to handle nonlinear viscoelasticity. At the end of the day, you end up with differential equations that you can't be solved, integral equations or differential equations that can't be solved analytically, and you have to resort to a numerical solver such as a nonlinear finite element analysis to make some sense of it, right? And basically, what people just do is the end result is this sort of engineering or realogical approach is what people use most of the time, right? We just run what tests we can, and we tabulate the data, and we interpolate between, right? Okay, so that wraps up the time temperature. I'll have all the questions to ponder up tomorrow, and the lectures will be up tomorrow. And this will be sort of, that wraps up the core sort of exam part, right? The parts of the course that you're likely to see in the long answer section of the exam, right? Fracture and texture, you might see a short answer on one of the topics, but it's not going to be a substantial part of the exam.